Hello everyone, welcome to JCE Connect. So in this particular lecture, I'll be taking the next case, that is a force exerted by a liquid jet on a moving curved vane. So in previous lectures and all, we have seen the force exerted by a liquid jet on a stationary curved vane. So here we are considering the force exerted by a liquid jet on a moving curved vane. In that we have taken the first case, that is for a single vane. Force exerted by a liquid jet striking on a curved vane when the vane is moving in the direction of jet. Let us consider a liquid of jet striking the vane. This is a pipe. Through this pipe a liquid is coming, and at the end of the pipe a nozzle is been fitted. As you know, the nozzle function is to increase the kinetic energy of the liquid. When it comes out of the nozzle, it will come with a high kinetic energy, and this jet of liquid will be in the form of a circular rod. It will be having a very high velocity, and the moment it strikes, then this plate also start moving with a velocity u. Okay, so both are moving here. So here a relative velocity will come into picture. So what do you mean by relative velocity? The relative velocity, the motion relative to a other body. So if velocity is been taken with respect to other entity, that is called as a relative velocity. Okay, so here we need to take the relative velocity. In previous cases and all, we have taken the absolute velocity. What do you mean by absolute velocity? The motion with respect to a fixed frame. So we have taken the motion of a jet with respect to the fixed frame. So there we have considered the vane as a fixed entity. With respect to that, whatever the velocity we have taken, that is called as a absolute velocity. Example, if you take the motion of a train with respect to the platform which is stationary, is called as a absolute motion. Where the train is moving with respect to the platform is a fixed entity. So with respect to that, the train is moving, that is called as a absolute motion. If the two trains are moving, say train A and B, then a relative velocity will come into picture. So relative to one another, motion of a body with respect to another body is called as a relative velocity. So here in these cases we need to take the relative velocity. So here a jet of liquid is coming out of the nozzle, will be having a velocity v. So this is having a velocity v. So before striking the vane, this velocity, what we call as an absolute velocity. The moment it strikes the vane, then the vane starts moving with a velocity u. Then it occupied a certain position like this, then it starts moving. As long as the jet will be striking the vane, this vane keep on moving with a velocity u. Then this u is called as a velocity of the vane. Then we have to calculate the again force in x direction as well as force in y direction. Okay, so the velocity of vane is u here. Then as the water gliding over the surface like this will be gliding over the surface after striking the vane. And again, assuming this surface is very smooth, there is no frictional loss. So then here also we are taking the absolute velocity. The jet will be striking with a velocity of v minus u. So here we have to take the jet will be striking with a velocity of v minus u, where this u is less than v, velocity of the jet. Then it goes out of the vane with velocity called relative velocity v minus u. Then again, if you resolve this one, you'll be getting a two components. So this is theta, and this component is v minus u cos theta, and this will be v sin theta. Okay, so again, as usual, we have to apply the impulse momentum equation to calculate the force in x direction as well as the force in y direction. Okay, so I think you understood this figure here. So again, in these cases we are considering the jet is also moving and the vane is also moving. So both are moving, so we have to take the relative velocity. Both are moving in the same direction, hence the relative velocity will be v minus u, and the velocity of the plate or the vane is considered as a u, which is less than the velocity of the jet. And the jet is striking with a velocity of v, then the plate starts moving, and the moment it strikes the plate, the water will glide over the surface of the vane, and this surface has been assumed as a very smooth. Hence there is no frictional loss here. There is no frictional loss, and the jet will comes out with a velocity called relative velocity v minus u. So here figure shows, alright, here figure shows a fluid of jet striking at the center of the curved vane, moving with a uniform velocity that is u, that will be less than v in the direction of jet. Let v represents absolute velocity of the jet, then a represents cross-sectional area of jet, and u represents velocity of the plate in the direction of jet. So when the jet strikes the moving vane, the effective velocity is the relative velocity. Effective velocity will become the relative velocity, that is v minus u. Okay, so this is what we need to consider in case of moving vanes. So in previous cases and all, so where we have taken the stationary vanes, so there we have taken only the absolute velocity. Again, I am repeating, absolute velocity means the motion with respect to the fixed entity is called as the absolute velocity. Since in these cases both are moving, jet is also moving and vane is also moving, so we have to take the velocity of the plate with respect to the jet. Okay, so here the effective velocity to be considered as, that is relative velocity v minus u. So further we have to apply the impulse momentum principle here. So further applying impulse momentum equation, so applying impulse momentum equation. Now we have to apply impulse momentum equation. You know impulse momentum equation, the force in x direction, that is mass flow rate into change in velocity. So here the mass flow rate to be taken rho a v minus u. So in previous cases and all we have taken rho a v, but in these cases we are taking the relative velocity. You have to take here relative velocity into change in velocity to be taken initial velocity minus final velocity. Again rho a v minus u initial velocity, that is, let us take this is a v1x minus v2x. Okay, so v1x and v2x. So again, from this figure we can consider here what is the initial velocity to be considered here. So in this figure, look at this figure. So here we have to take v1x to be taken as v, that is the initial velocity with which the jet is v1x to be considered as v minus u. This velocity it is striking. When it strikes, it becomes v minus u, that is a relative velocity. With relative velocity it is striking. Then v2x is here, minus v minus u cos theta. We'll get this one. Okay, in x direction. So we are calculating force in x direction. So mass flow rate, we have to take the mass flow rate or mass of liquid striking the plate, that is rho a v minus u. We have to consider this one. Okay, then here rho a v minus u into v1x will be v minus u. With this velocity it is striking initially, minus of v minus u cos theta. Okay, so here it is striking with v minus u initially. Then final velocity will be what? V minus u cos theta, but in the opposite direction. Then what it becomes rho a v minus u into bracket v minus u plus v minus u into cos theta. Take v minus u out, into bracket 1 plus cos theta. This is force in x direction. Okay, so this is a force in x directions. So we want force in x direction only. This is the answer. Then, as we know how to calculate the efficiency, so now calculate the efficiency of the jet. So efficiency of a jet formula, we have output by input. Please make a correction. In previous lectures I have taken this is a reverse, that is input by output. So it's not input by output, this is output by input. Please make a correction. So efficiency of the jet to be calculated, output energy divided by input energy. So here what is the output energy? First we have to take the input energy. The input energy will be what? Input energy will be kinetic energy, what we are supplying per second. That is input energy. Here we are supplying the kinetic energy, that is the input energy. So how it can be calculated kinetic energy? The kinetic energy can be calculated half mv square is a kinetic energy, but it is to be taken per unit time. Then it becomes half rho av into v square. So mass per unit time will be equal to rho av into v square. It becomes rho a v cube. Rho a v cube. Now output energy. Output is what? Work done per second. This I explained in the previous lectures. What is work done? When you say the work done, we say the work is being done when a force acting on any body, if the body get displaced, then we say the work is being done. So in this case the jet is striking the vane is moving, means the work is being done. Hence work done per second, that is to be taken force into velocity. So this we have derived. So force, that is force in x direction acting, that is force exerting by the jet in x direction, into velocity of plate, that is Fx into u. So I'll substitute here Fx already we have calculated here. Fx rho a v minus u square 1 plus cos theta into u. Then work done per second, rho a v minus u whole square 1 plus cos theta into u. Okay, then the efficiency of the jet can be calculated. Substitute here, that is work done per second divided by kinetic energy per second. Then rho a v minus u whole square 1 plus cos theta into u divided by half rho a v cube, kinetic energy. Okay, so simplify this one, you will get 2 times of v minus u whole square into u 1 plus cos theta whole divided by v cube into 100. So this is the equation you get after simplification. This is the efficiency of jet. Okay, then further simplification, if you simply that one, means for maximum efficiency, how much is the maximum efficiency? For maximum efficiency, that is eta max. When we get eta max, we want eta max when differentiation of efficiency with respect to the velocity of the plate will be 0. Means the efficiency of the jet it depends upon the velocity of the plate, how fast it moves. So it depends upon the velocity of the jet. Means suppose if you take a turbine, this is a impeller shaft, then the blades are mounted like this, then the jet will be striking. So this is the input energy what you are giving, that is the kinetic energy of the jet. Then this will be striking the blade, then the blade starts moving with a velocity u, it moves forward, then the next blade will come and stand before the jet, again that also receives a force, then that also moves, then again the next blade will come and stand before the jet. So this will continue. Then here the energy is being supplying from the blade to the impeller to the shaft to the generator. So the generation of power electricity depends upon this blade velocity. Okay, then the efficiency of the turbine, it depends upon what? The velocity of the vane. Okay, so here the efficiency of the jet, it depends upon what? The velocity of the plate. If we differentiate the above equation, if we differentiate this equation with respect to the vane velocity, then we get the maximum efficiency. Then 2 minus 2 divided by v cube from above equation, 1 plus cos theta into 100, then d by du into bracket v minus u whole square into u equal to 0. So in this equation we have taken this only, v minus u whole square. In this equation we have taken only v minus u whole square into u. So this term, that is 2 by v cube 1 plus cos theta, it cannot be 0. Okay, so take only this term now. Only take this term and differentiate. So if I take d by du v minus u whole square into u, then differentiate this one. So let us apply here product rule, that is u into v. So v minus u whole square into 1 plus differentiate u. First I taken this, then differentiation of u will be 1, then take a u, then differentiate that this term 2 into v minus u, then differentiation of minus will be minus 1 is equal to 0. Then what you get, v minus u whole square, then minus, simplify this one, 2u v minus u is equal to 0. Then v minus u whole square is equal to 2u v minus u. Then v minus u will be what? So this get cancels, you will get 2u. Then v equal to what? You get 3u. Then u will be v by 3. So velocity of the plate will be v by 3. When the velocity of the plate becomes 1/3 of the velocity of the jet, means this, when velocity of plate is equal to 1/3 of velocity of jet, then the maximum efficiency can be achieved. So substitute this u, that is u equal to v by 3 in this equation. Okay, we have to substitute that v by 3 in this equation. So what we get if we substitute, then the maximum efficiency will be, when you substitute, we get 8 by 27 into 1 plus cos theta. Look at this equation. If I substitute the value of u here, v by 3, substitute v by, wherever u is there, you substitute v by 3 and simplify it. If you simplify it, you will be getting 8 by 27 1 plus cos theta. Okay, then into 100. This is the maximum efficiency. So many times the question will be asked, prove that a jet striking a single curved vane at the center moving, the maximum efficiency will be 8 by 27 1 plus cos theta. Okay, suppose if theta is equal to 0, when you get a theta equal to 0, see, in this case, when you get a theta equal to 0 here, see, this is the curved vane, the jet is striking here, and after striking, this is the velocity of the jet exiting, making an angle of theta. When this theta equal to 0, means, suppose this is the vane, see, this is the vane, the jet is striking in this vane. When the jet strikes, and then the water glides over the surface, and if it exiting like this parallel to the incoming jet, if these two are parallel, so in that case the theta will be 0. When the theta 0 means this plate will be what kind of plate it is? It is a semicircular plate. This is a semicircular plate. So in that case, when theta equal to 0 here, so theta equal to 0 means semicircular vane. Semicircular vane. When theta equal to 0, efficiency 8 by 27 1 plus cos 0 is 1. Then what you get here? 16 by, you get 16 by 27. Okay, or efficiency you will get 59.2%. This is for single vein. Okay, so many a times this question has been asking in exams. Prove that for a semicircular vein the jet is striking at the center, the efficiency is 16/27. So this is the proof. So when they are asking for a semicircular vein, you have to take theta equal to 0. If they are asking only for a curved vein, prove that 8/27 1 plus cos theta into 100. Just you take the curved vein like this, then draw this figure like this, then derive it. If they are mentioning particularly semicircular vein, derive this equation, then you substitute theta equal to 0. So theta equal to 0 means it's a semicircular vein. Okay, so here the jet will be going out of the vein by making an angle equal to 0, that is theta equal to 0 like this. Okay, when theta becomes 0, you will be getting this one. Eta max is 59.2% or 16/27. Eta max equal to 8/27, cos 0 equal to 1, you will get 16/27. I hope you understood this one. Okay, this is moving vein derivations, very important. So I'm creating here very important derivation. Derive an expression for efficiency, that is they'll be asking like this: 1 plus cos theta into 100. Many a times question will be asking. So here I can show you the question. You can see the question here in exam. Show that when the jet of water striking symmetrical moving curved vein at the center, the maximum efficiency for a semicircular vein is 8/27 1 plus cos theta. Okay, so this is the derivation, that one. So this is the 1 plus 8/27 1 plus cos theta by 1 plus cos theta into 100. Okay, so look at here like this. If they are asking in terms of efficiency like this, percentage, you 59.2%. I hope you understood this one. Okay, practice this derivation. This is very important. I'll be taking a next case, that is a force exerted by a jet of water on a series of curved veins. And in previous lecture we have seen the force exerted by a single curved vein when the jet was striking at the center and the vein was moving. Okay, so like this, if this is the impeller of the turbine, it is coupled with the shaft. If suppose a single vein is mounted like this and the jet is striking with a velocity v at the center of the vein, and only one vein is present on impeller, when the jet strikes, this starts moving in this direction. Okay, in this case we have obtained the efficiency generated by the jet was 60%. We have seen in a previous lecture, and we have obtained the efficiency. Okay, but what happens in this case? So the force exerted by the jet on a single moving curved plate, actually it is not practically feasible. Only by having only a single vein on a impeller, we cannot achieve the required efficiency of the or required power. And what happens? This case is only a theoretical case, because in this case what happens? The distance between the plate and the nozzle, that is a nozzle provided for the jet, will be constantly increasing at the rate of u per second, which in turn would require continuous lengthening of the jet, at this rate in order to strike the plate. So this difficulty, however, may overcome. So whatever the difficulty we were having here, that may be overcome by having a instead of a single vein. So if we have a series of veins mounted on the impeller like this, so there is a continuous series of plates arranged at a fixed distance apart. These are at a fixed distance apart, so that each plate moving with a velocity u. So that each plate moving with a velocity u, and further what happens here, that when the jet strikes a plate, and due to the force exerted by the jet on the plate, the wheel starts moving. The moment it strikes the vein, it moves forward with a velocity u, and then the next blade will come and stand before the jet. Again it also receives the force from the jet, that also moves with a velocity u. Again the third blade will come and stand before the jet, that also receives the force. Again it moves forward. This will continue, hence a continuous rotation of the impeller will takes place. And when it continuously starts rotating, it is coupled with the shaft, then the shaft in turn coupled with the generator, hence the production of electricity. But in this case what happens, so there is a continuous of there is no continuation of or continuous rotation of the impeller will takes place. Once the jet strikes, it may move and come and stand over here, and it may come or it may not come. So in this case the efficiency of the jet will be less here. We cannot achieve the required one. So this case is only theoretical case, it is not practically feasible. To overcome that one, so next arrangement will be like this: a series of vanes mounted on the periphery of the impeller like this. Okay, so in this case we get the continuous rotation of the impeller. So let us consider this case. Consider a jet of water of velocity v and having a jet diameter d striking the vane at the center, and the vane is moving with a velocity u. Okay, so let us derive the equation for this one. That is a force exerted by a jet of water on a series of curved vanes. Okay, so this is very important, and this is practically feasible also by having this kind of vanes. Actually that if you look at the turbines, that is a Pelton wheel turbine, the series of vanes will be mounted over the impeller like this, and the force receiving by the vanes one by one, that is the jet striking the vane will move forward, then the next blade will come and stand before the jet, that also receives. So this will continue, hence the force is being that is the energy is being transferring from the vanes to the impeller to the shaft to the generator, hence the production of electricity will takes place. So in this figure there is always one vane as the other, one vane or as the other facing the jet, and the entire fluid is being utilized here. So the mass of water striking up per second equals, in this case the mass of water striking. So what happens here, in this case the mass of water coming out from the nozzle, per second, and is always in contact with the plates. That is whatever the mass of water is coming out of the nozzle is always in contact with the plates, because one by one the vanes are receiving the jet, but here the jet may contact or may not contact with the vane, because once it strikes it goes on moving, and it lengthening of the jet may takes place here. So after certain time the jet may strike or may not strike in this case. Okay, so contact with the plates, when all the plates are considered, all the plates are considered, hence mass of water per striking, mass of water strikes per plate, mass of water strikes per second, can be written as per second, mass of water strikes per second on a series of plates, can be given as rho AV. Okay, here we will take rho A, mass per second. This is mass of water striking per second. Let V represents velocity of jet, then D represents dia of jet, then A can be written as pi by 4 d square, area of the jet, and U will be velocity of the vane, Then further, if we apply impulse momentum equation for this one, if you apply impulse momentum equation here, applying impulse momentum equation in the direction of jet, impulse momentum equation, then the force exerted by the jet in the direction of jet, that is in x direction, it is a force exerted, let us take this is a x direction, the force exerted by the jet on the vane in x direction can be analyzed by using the impulse momentum equation here. So I am applying impulse momentum equation. You know the impulse momentum equation, that is Fx equal to the rate of change of momentum in the direction of jet, So that is mass per second into initial velocity minus final velocity. So further, if we solve, so Fx equal to mass per second will be taken rho AV. So remember, in series of vanes we have to take rho AV, but if it is a single vane we have taken relative velocity there. So but here you have to take the absolute velocity rho AV into bracket. Initial velocity will be what? Again, initial velocity, the jet is striking with a velocity v, the vane is moving with a velocity u, but in this case initial velocity taken, that is v minus u. Okay, because vane is also moving, jet is also moving, both are moving, we have to take the relative velocity as the initial velocity. So that is v minus u, then plus v minus u into cos theta. Because why cos theta? So look, this field again, it is striking at the center here. When it is striking, the jet will exert like this. Then if you resolve this one, if this is making an angle of theta here, what is this component? This, if this is striking at this, but this at the vane, the velocity is v minus u, initial velocity, and the final velocity again it is leaving with a velocity of v minus u. So like this it is, the jet is striking like this, it is v minus u, this is also v minus u. If you take this as angle theta, this component is v minus u, cos theta. Okay, then v minus u plus v minus u cos theta. If you solve this one, you will get rho a v minus u, rho a v minus u plus v minus u cos theta. If you take it out, rho a v minus u 1 plus cos theta, you get like this. Okay, then work done per second. Work done per second, we know the formula, force into velocity of plate. The force is already, we have calculated this one. This is the force exerting by the jet. Then Fx equal to rho a v minus u 1 plus cos theta into velocity of plate. Then next, efficiency of the jet. Efficiency of the jet, that is eta. Then efficiency of the jet can be calculated, that is work done per second divided by kinetic energy per second, that is output by input. So input, what we are giving here, input we are giving kinetic energy, that is kinetic energy of the jet, that is the input, and the output work done, so that is output. Then you know how to calculate the kinetic energy of the jet. Kinetic energy per second will be rho a v cube, half rho a v cube. Then work done per second, already we have calculated work done per second. Substitute this one here, rho a v minus u 1 plus cos theta into u divided by half rho a v cube. Okay. Then into 100 you will get the efficiency. So this is the efficiency equation. Then now we have to calculate what is maximum efficiency. If you solve this one further, you will get 2 v minus u into u divided by v square. Then we get 1 plus cos theta as the equation into 100. If you simplify this one further, we get this equation. Then for the maximum efficiency, we know d eta by du equal to 0. So this, if this is to be maximum, we differentiate this equation with respect to the velocity of the plate. So the efficiency of the jet depends upon the velocity of the plate. Differentiate with respect to u. So when you differentiate with respect to u, so if I take it the constant terms out, that is 2 by v square into 1 plus cos theta, then I have to differentiate only d by du, v minus u into u is equal to 0. This term, that is 2 by v square 1 plus cos theta, it cannot be 0. Okay, so you cannot make it as a 0, so you take it out, that is v minus u into u, differentiate with respect to u, then apply the product rule here, then differentiate. So when we get d by du, v minus u into u is equal to 0. If I differentiate this equation, then what I get, u by first v minus u into 1, then plus u, then differentiation of this will be minus 1, then what you get is equal to 0, then v minus u equal to 0, then v equal to, we get a 2u, from this what I get, v plus 2u, sorry, v minus 2u, then I'll get a v equal to 2u or u equal to v by 2. Hence for a maximum efficiency of the jet, or maximum efficiency of the wheel, you can say it is a wheel, maximum efficiency of the wheel, the peripheral speed, that is u. Peripheral speed means u, this one. Peripheral speed means this peripheral speed. It depends upon the velocity of the vane. Speed is 1/2 of the velocity of the jet. 1/2 of the velocity of the jet. Substituting the value of u in this equation. Substitute that value of u in this equation. Say equation number 1. Substitute u equal to v by 2 in equation 1. Therefore, maximum efficiency, what we get if we substitute 2 into v minus v by 2 divided by v square into v by 2, 1 plus cos theta. If you simplify this one, you will get half. Simplify this one, you will get half 1 plus cos theta. This is the maximum efficiency for a series of vanes. So if you again into multiply, you will get 100% efficiency. So when theta is 90 degree, so it becomes a flat vane. When theta is 90 degree, means suppose theta is 90 degree, efficiency will become, when cos 90 is 0, then half is 0.5, 0.5 into 100, you will get efficiency as a 50%. When theta is 180 degree, this is for semicircular vane. Efficiency you get when theta is 180 degree or 0 degree. 180 degree or 0 degree. So if for 0 degree, what is cos 0? Cos 0 is 1. Then you will get 100% efficiency. Means if theta becomes 90 degree, means when the jet strikes at the center, the jet will deflect at an angle of 90 degree. Like this. That is theta. Okay. If jet is 0 means if it is a curved vane like this, when the jet is striking, then after striking the jet will deflect like this. It comes out with an angle of 0 degree. So this is possible only in a semicircular type of vanes. If the jet is striking like this and leaving by making an angle of 0 degree. When it becomes a 0, if you substitute the value of that theta here, you will get 100% efficiency. Means, so to achieve 100% of efficiency, we have to have a vanes on a impeller like this, circular vanes or semicircular vanes like this. So by having a semicircular vane, we can achieve the 100% of efficiency. Okay. So that is been proved here. Okay. When the jet strikes, it leaves by making an angle of 0 degree like this. Okay. This is semicircular vane like this. And the jet strikes. After striking, the water will glide over the surface like this. Then it will exit like this. Then suppose this is v minus u, but it is making an angle of 0 here. Okay. So when theta is 180 or 0 degree, it means semicircular vane, and the efficiency will be maximum, that is 100%. When the efficiency is maximum, when the vane velocity becomes half the jet velocity, then you will get the 100% efficiency. This is very, very important derivations. It is many times asked in an exam. Very, very important, this derivation. Many times it is asked in the exam. So this is that is a derive an expression for force exerting by a jet, a series of vanes. So I'll show you this question paper. In this particular question paper, they asked the single vane.
prove that is show that the efficiency of that is a jet of water striking a symmetrical moving curved vane at the center. The maximum efficiency for a semicircular vane is 8 by 27 1 plus cos theta. This is for a single vane. So like this, a series of vane is also been asked in exam. So that is, I'll show you here. See here in this particular problem, here they asked, look here, show that maximum efficiency of the jet striking a series of curved vanes moving in the direction at an angle pi with a velocity u is maximum is equal to 1 plus cos pi by 2. Okay, so that's the same we have derived here, 1 plus 1 by 2 1 plus cos theta. Okay, 1 plus cos theta by 2 into 100, that is the efficiency. So this derivation is very important. So you have to remember, only thing is in this case the mass of water striking per second will be taken rho a v, but in a single vane we have taken this term rho a v minus u. Okay, so there the entire water was not being utilized, that is completely. Here the entire quantity of water is utilizing completely, because when we consider all vanes together, so when the jet is striking, then this vane moves forward, again the next blade will come and stand before the jet. So this impeller will be completely in rotation, hence the generation of power here. Okay, so please practice this derivation, this is very important. Okay, so only thing you have to apply the impulse momentum equation here. So after applying impulse momentum equation, finally you have to derive the maximum efficiency. For getting a maximum efficiency, you have to differentiate the efficiency with respect to the vane velocity. So then you get the equation, that is the velocity of the vane is equal to half the jet velocity. Then substitute back in equation, then you will get the maximum efficiency. Then finally, if theta equal to 90 degree, that becomes the flat vane case. If theta is 0 degree or 180 degree, it becomes a semicircular vane. Then you will get the maximum efficiency as 100%. So 0 degree means when the jet is striking and leaving an angle of 0 degree like this. So if such kind of vanes are being provided on the periphery of the impeller, so definitely we can achieve the 100% of efficiency. If we have flat vanes, if it is deflecting by an angle of 90 degree, so we cannot achieve 100% efficiency, we can achieve only 50% efficiency, means 50% of the jet may not be striking the vane. We can say the 50% will get waste. Okay, so in this case, so we can achieve 100% of efficiency. I hope you understood this one. So practice this derivation. Thank you.